was a talk, Negative Dependence on Lorentzian Polynomials by Brändén.
Thank you. Thank you for showing up, and thanks for the organizers for inviting me to give this talk. And well, during this semester you've already heard a few talks about Lorentzian polynomials under different names. Maybe Nima and his collaborators have called them Lorentzian polynomials. No, sorry, completely log concave polynomials. But the one who started studying them was Leonid Gurvits, and he called them strongly log concave. But they should be called.
No, but originally I called them Alexander Fkd.
Yeah. This is what I.
Yes.
So, but today I'll try to zoom in on one topic that we brought up in our paper, namely negative dependence, and what Lorentzian polynomials has to say about that. And maybe fitting for this workshop is that I will focus on the random cluster model, or the Q-POTS, the Q-state POTS model. Okay, so we will be looking at discrete probability measures. So we have a discrete probability measure mu. On the collections of subsets of a finite set E. For our purposes. And then we want to investigate negative dependence properties, and we do that through the multivariate partition function. So we have the partition function. And this is Z mu, which is then the sum over all subsets of E. And then take x to the a, where here x to the a is just the product of all the variables that are in. Okay. So this is a multivariate, multi-affine polynomial. So all the variables appear at most to the power 1. So then, what is positive and negative dependence? So positive dependence tries to model attracting particles. We think of having particles at each of these sites indexed by E, and then positive dependence models attracting particles in terms of properties of mu, and then negative dependence models then repelling particles. So maybe the simplest instance of positive and negative dependences is positive and negative correlations. So I guess it's positive correlations or pairwise correlations is that the probability that two probability that EG are present or is greater or equal to the product of the individual probabilities. That I is present times the probability that J is present. So this is the probability that we would see if these events were were independent, but since we have some attracting particles, they want to. We have a greater probability of that both are present. So we have some attractions going on, and the same thing with negative negative correlations is then when we have the opposite sign. And we also have, so these are rather weak positive dependence and negative dependence properties, and we can get stronger if we look at positive association instead. And this is the property that the expectation product of two functions should be greater or equal to the product of the expectations. And this should hold for increasing functions. And the same, we also have then negative. Well, negative association is a bit more subtle. So it says that the reverse inequality holds, but for increasing functions. Increasing f and g, but depending on disjoint set of variables. So what I mean by that is that we can partition the set E into two sets, and f only depends on one of the sets, and g depends on the complement of the coordinates. Okay, so how would we? So in terms of the partition function, this so positive and negative correlations would so the probability that I is present, well, this is what we get if we differentiate the partition function with respect to I, because then all the terms that do not contain I disappears, and we're left with ones that contain I. So these correlations can be interpreted as an inequality of the partition function, namely that I use partial I to denote the partial derivative with respect to I. So then the positive and negative correlations are interpreted as this inequality differential equality, where we look at the vector of all ones. And if we look at some other vector, we also get positive and negative correlations, but for the measure where we impose some external field with positive coordinates of the x-axis. Okay. So what is the random cluster model? So it was introduced by Brändén and Castellane in 72. So we have some graph G. On a finite set. And then we have some parameter Q, which is greater than 0. So here in this talk, Q does not have to be an integer, but it can be any real positive number. So it's not any real space. So, and then we define a measure by saying that the probability of a singleton, of a set A, is proportional to first the product. So we have weights too. So we have weights W, E, which are positive for each edge. And then we take Q to the number of connected components. So K of A is the number of connected components of the graph with edges A.
Product is over edges E and A, not an E and P, right?
Yes, otherwise it will be trivial. Thanks. So this is the random cluster model, and it's also the QPOTS model where we have this external field here. So we've seen that yesterday and the day before yesterday, I guess too. Okay, so let's have a look at, so for Q less than 1, this random cluster model favors few connected components, or few clusters. But for Q greater than 1, it wants to have many connected components. And so this sort of hints to that for Q less than 1, it should be negative dependent, and for Q greater than 1, it should be positive dependent. And maybe this is more easy to see where if we look at the quotient, if we take mu of look at this quotient, then this external field disappears, and we only get Q to the connected components of A intersected plus. And now this is a supermodular function, so we will get that this is less than or equal to 1 if Q is greater than 1, and it's greater or equal to 1 if Q is less than 1. If I got the signs right, and I think I did. And then there is a famous theorem by Brändén and Castellane and Ginebra, namely the Fkd Theorem. So this says that if this property holds, that the top is less than or equal to the bottom, and this is called the negative lattice condition. If this holds, then the measure is actually positively associated. So this says that for, and direct consequence is that for q greater than 1, mu is positively associated. So this is easy. Q greater than 1 is easy in this respect. But for, so the long-standing conjecture is that for q less than 1, mu is negatively dependent. And what do I mean by that? Well, so this is maybe a loose conjecture, but it should be, in particular, it should have negative associations. And more weakly, it should satisfy, it should have negative correlations. And it should have this property. Okay, but
Question?
yep.
So this so-called Reimer's inequality doesn't help here?
No. So this is more for, well, I guess, well, it was only proved for product measures, I think. And well, now they proved it for more, a little more general.
So, and in Fkd only the supermodularity method or the structure was important? So say I have any function q to any function which is exponential. Yeah. So only that matters.
Yeah. So only this negative lattice condition, positive lattice condition is relevant here. So this is a very general theory, well, easy to apply. So you only need this very local theorem implies a global theorem like positive association. And it's very applicable, well, very useful in many situations in
But
combinatorics.
this is not a local condition. I mean, supermodularity is like convexity sometimes, right?
This is local, right? You only look at.
But this is true for.
Oh wow! No, you can see that you actually only need to look at pairs of. Yeah, you can define it locally. So
Yeah, no, I know what you're saying, but I mean, this is like convexity, so you can define it locally.
Yeah.
It gives you a global condition.
And it gives you. Yeah, sure. Okay. So. So we also talk about zeros of partition functions in this workshop, and so many of these instances of negative dependence can be proven by looking at the zeros of the multivariate partition functions. This is a theorem that is 10 years old. And it says that if we have a measure mu and z mu is stable, meaning that z mu is non-vanishing whenever the imaginary parts of the variables are positive for all I, then mu is negatively associated. And many more properties. So it satisfies most virtues of negative dependence that you can think of. So this is a very, very powerful class, and you can prove a lot of negative dependence properties from this. However, it's not. You can quickly see that it's not applicable to this case. I think only for sort of trees. If you have a cycle, then you're screwed. So what are we going to do? So we want to relax this property. And how do we want to do it? Wherefore, we can look at this easy, simple lemma. So if we have a polynomial p with non-negative coefficients, which is homogeneous and quadratic, then the following are equivalent. So the first is that indeed P is stable, and the other one is that if we write P as a if we let Aij be the Hessian, then this matrix Aij should have exactly one positive eigenvalue, or as at most, this is equivalent, as at most one positive eigenvalue. Well, because it has non-negative coefficients, then if it's not entirely zero, or then it has a Perron eigenvalue, so it has some positive eigenvalue. And if it's non-singular, then it has the Lorentz signature, meaning that it has exactly one positive eigenvalue and the rest of the eigenvalues are negative. And this is where these Lorentzian polynomials appear for us.
Non-negative, not necessarily negative, non-negative.
Well, if it's non-singular, I said.
Ah, you say non-singular.
Yeah. So, so we first defined strictly Lorentzian polynomials, which is then going to be an open set of polynomials. So a polynomial P homogeneous degree D polynomial. With non-negative coefficients is strictly Lorentzian if first all possible coefficients are positive, and by possible I mean that we already have the constraints that it's homogeneous of degree D, so all possible coefficients should be positive, and more importantly that whenever you differentiate your polynomial along the coordinate axis D minus 2 times, you should get a polynomial of this type, namely a stable polynomial, or well, a strictly stable polynomial, or a matrix with a symmetric matrix with a Lorentz signature. So for all say I1, I2, ID minus 2, positive integer or non-negative integers, or positive integers, the polynomial, the quadratic di1, di2, di minus 2, p has, well, if we look at this as a as a symmetric matrix, then it has the Lorentz signature. Meaning it has exactly one positive eigenvalue and the rest of the eigenvalues are negative. Does that make sense? It looks a little ad hoc maybe, but it turns out to be the right definition. So we consider then that strictly Lorentzian polynomials are the polynomials with all coefficients are positive, and whenever you sort of whenever you project it down to a quadratic using derivatives, then you get a polynomial with a, well, quadratic with a Lorentz signature, which is equivalent by this lemma to being sort of a stable, strictly stable polynomial. So it is indeed a relaxation of this property of being stable. And we shall see that it is a rather nice class. So I have 20 minutes left.
Yes.
Good. Okay, so what is a Lorentzian polynomial then? So, well, so the closure of the set of strictly Lorentzian polynomials will be called the space of Lorentzian polynomials. So a polynomial is Lorentzian if it is the limit of strictly Lorentzian polynomials. Okay? And this can maybe looks hard to work with, but we shall see that we can get a nice characterization of Lorentzian polynomial.
B0.
Yeah, it's a matter of taste. If you, yeah, it could be 0. Yeah, identically 0. But usually one looks at this projectively, and then we can sort of normalize this coefficients. So, yes, so let's look at some. So by just looking at this definition now, so when is a, so if we have a, if we now have a bivariate polynomial, with all the with positive coefficients now, then this is Lorentzian if and only if we have these inequalities. And why is that? Well, what is the definition? The definition is that is strictly Lorentzian. The definition is that all the coefficients should be positive. Well, we assume that, but so we only have to check when we differentiate down to quadratic. But if we differentiate down to quadratic, we are going to get exactly these coefficients, but with a 2 in front of the AK. So this quadratic being stable is the same as, well, this the corresponding matrix having exactly one positive has exactly one positive eigenvalue is equivalent then to this 2 by 2 matrix having negative determinant. It should have one positive eigenvalue and one negative eigenvalue, so the corresponding 2 by 2 matrix should have negative determinant. And this is exactly what you get. And some of you should recognize this inequality. Grubitz does. So these are the Newton inequalities, or the ultra-log concavity. So these are the Newton inequalities which are satisfied by polynomials with only real zeros. Univariate polynomials with only real zeros. So for bivariate polynomials, which could be seen as affine univariate polynomials, then the strictly Lorentzian property is equivalent to satisfying the Newton inequalities, which is a sort of a nice relaxation of the class of real-rooted polynomials. And this will be useful for us later. Okay, so in order to work with these Lorentzian polynomials, we want to get a nice equivalent condition. So for this, we want to define what an M-convex set or a polymatrod is. So if a collection, finite collection of vectors, we call it J. So a finite collection of integer vectors is an M-convex set, or the basis of a polymatrod. If the following axiom holds. So, for all alpha and beta in J, and any index so that the coordinate in alpha is less than the coordinate in beta, then there is an index, say J, such that instead alpha J is greater than, that the coordinate in alpha is greater than the coordinate in beta, and such that we can move from alpha to beta in 2 steps. So we get, so say that we have alpha here, and here is here you would have beta minus ei. So, yeah. So in other words, we should have that alpha. So we should get. Oh, sorry, we don't. Sorry, we don't need this part. This is the symmetric one. So we should be able to go 2 steps and then fall into this set J again. So that alpha plus EA. Alpha plus AJ minus EJ is in J again. So let's take this again because it got a bit confused on the way. So an M-convex set is such that the following sort of basis change axiom holds, so that if the alpha coordinate is less than the beta coordinate for some I, then we should find another index J with greater alpha coordinate, so that we can move, so that we can add 1 step in the ith coordinate and subtract one in the jth coordinate, so we appear in the set again. So if you think about 0, 1, if J is just 0, 1 vectors, then this is equivalent to the basis exchange axiom for matroids. Okay, so that's why it's called equivalent to polymatroids. Okay. And now we can characterize Lorentzian polynomials. So a polynomial with non-negative coefficients is Lorentzian if and only if. So first, the support of f, or support of the polynomial p, which by definition is the So the support, so it's Lorentzian if and only if the support is a polymatroid. So this is a combinatorial condition, and the next condition is then that this relaxation of that the projections should have the Lorentzian signature. So the so the other one is that these projections has at most one positive eigenvalue. So this is that the corresponding closed property of having Lorentz signature.
What is the difference between definition? So your definition of Lorentzian polynomial was if you differentiate, you get that.
But you have positive eigenvalues then, positive coefficients.
I see.
So we defined an open condition so that we don't. So this is then non-trivial to sort of see that if you. So what kind of supports do you get when you don't require? Well, when you relax this property, and what you get is actually exactly the M-convex function. So there's a converse to this, that any polymatroid is going to appear as the at the support of on an M-convex. So conversely,
Is homogeneous statement?
In the definition you also had
Yeah.
homogeneous.
homogeneous. So conversely, if J is a polymatroid or an M-convex set, then the generating polynomial suitably scaled is Lorentzian. So this class of polynomials is intimately connected to polymatroids and matroids. So now another property which is important is that it's closed under changes, linear changes of variables where the corresponding matrix is non-negative. So if P is Lorentzian and A is a matrix, a suitable matrix with non-negative coefficients, then if we do this change of variables, then this is Lorentzian again. So, so if we have a Lorentzian polynomial, then we can, for example, identify a bunch of the variables so that we come down to a polynomial of a bivariate polynomial, and then this bivariate polynomial has to satisfy these Newton inequalities.
So what's the, where does A lie? A is
So I said it should be suitable so that it should have, if P has n variables, it should have n columns, but otherwise.
By the way, which theorem precedes? Is it that one corollary of that one, or?
Yeah. So no, so we start by proving this actually. Sort of.
No, but if you have this one, because this one gives you the main beauty of this, it changes, gives you way to perturb polynomials.
Yeah.
Yeah, this is how you do it.
And yes, this is sort of how we do it.
Because this is actually how I was dealing. I wanted to avoid complex analysis.
Yeah.
And this is how I did the perturbation in the original problem.
So now we can collect some more properties. So if we apply, okay. And we also have this that if P is Lorentzian, then we have this almost negative correlations. So we have the IP times the, so if we take P times di djp, then this is less than or equal to 2 times the IP times djp. So we almost have negative correlations, but we have to pay the price of a 2. Okay, so how does this all apply to the random cluster model? Well, if we now have a random cluster, so if mu is a random cluster model with q less than or equal to 1, then the partition function is actually Lorentzian, or the homogenized partition function.
Sorry, question. Is this inequality, does it hold on Rn or on the positive orthant?
Positive.
Sorry, positive order. Sorry, you cannot see this, right? Ah, you can see it there. So So if we homogenize the polynomial, the partition function of the random cluster model for q less than 1, then this is indeed Lorentzian. So what do we get? We cannot prove the negative correlation conjecture, but we can almost prove it. We can prove it with a 2. But we get the one non-trivial fact that we get is that the rank, so the rank generating polynomial is satisfied Newton's inequalities, which is also a desirable negative dependence property. So let's phrase this. So, so again, with the same hypothesis as before, if now Rk is the probability that the set A has size k, it's the rank. Then we have the Newton inequalities for this Rk. Which is sometimes a useful property if you, for example, want to look at when convergence into to normal distribution. This is usually enough to prove convergence to normal distribution, which I don't know if that's been considered.
What is that in
Pardon?
What is n in this case?
Ah, thanks. So here n is the number of edges. So I think I stopped it. Thank you very
much. Questions?
How this statement that polynomial is Lorentzian, is it hard to prove?
No.
What is the?
This is the beauty of it all. That so one of the defining properties is that the support is a matroid sort of, or a polymatroid, and matroids and polymatroids are closed under taking conditioning, or so. And conditioning is the same as taking partial derivatives.
So here you.
So we only have to prove, yeah.
Here you have that specific.
So all these matroid questions that we can solve with this, we just have to prove for rank 2 matroids. And rank 2 matroids are very simple. They are just like
the last for that specific parts model.
Yeah.
This is.
But this is also like if you differentiate with respect to A, you to a variable here, you get a random cluster model for one edge contracted, right?
So one question which kind of I was curious when I was trying to understand your paper. So in homogeneous case there is this equivalent way to say what is polymatroid. You write those whole-like inequalities. So, so can you go straight to the things which is kind of, in my opinion, easier to understand than the jump system. So there is this equivalent condition.
Yeah.
So and work directly with that things, which is almost like, it feels almost like perfect matching situation.
This is what we get.
Huh?
So this is a polymatroid, but
yeah, but instead of working with that you use that proof for jumps thing.
Yeah, but this is equivalent. This is like
but
easy. Right. So, but yeah, you could work with that instead, I think. But yeah, they're all the same. Yep.
So this
else give some new inequalities for even the q equals 1 case, the independent? Or does it give some?
So you mean, so the independent sets you get by letting q go to 0?
No, q equals, no, not that kind of independence. Q equals 1 is.
So q equals 1 is just, then it's just a product measure.
Right, but does.
No. So then we don't, then we just get the binomial, then we get,
The theorem had q less than or equal to 1.
so then we would get 1 is greater or equal to 1 here.
Not very useful.
So
So if I substitute instead of x, e to the y, and then I look at the function that I get, this is not convex, right? So this is convex up to a factor of 2. Is that what your theorem implies? Because in the case of real stable polynomials, if I do this substitution, I get a convex function.
so the logarithm of this is concave.
It's still despite the factor of 2?
Or the,
No, I'm talking about making the substitution xi as e to the yi, and then looking at the function in the variables yi.
And what? And so what is, why is stability there? So what is the statement about stability? So you do the substitution,
Yeah.
and log is convex. With that substitution.
No, but we have to still prove that the Hessian of this is positive definite. So,
no. That's one theorem. The Hessian is going to be Lorentzian again.
yeah, so it's not positive definite, right? But it still has this fact, within a factor of 2, it is...
But it's like, it's convex, it's Hessian is negative if you have the original variables, but you've already made the substitution, right? And that's what changes things.
So there's a large class of, so these stable polynomials, they satisfy this with a factor 1 here.
Yeah, so the nice thing is that I can optimize over those stable polynomials. You know,
Even better,
my
yeah.
question is, can I optimize over these kinds of functions as well?
Optimize
Yeah.
what?
I mean, things like entropy, which I was talking about.
But I think what you were talking about depended only on the negativity of coefficients.
No, it also required convexity of the log partition function after you made this.
But that only requires non-negativity of coefficients. That property.
Okay, that's good.
Yeah.
Maybe save this for the...
That is not, has nothing to do with stability.
Do you know any polynomials where you have that inequality but reversed with bigger than or
That
equal
is the
to
sum
y
of
to
convex
for
and local.
all vectors in the positive orbit?
That was.
Say that again?
So you have it less than or equal to 2 times that.
Yeah.
But then do you have the reverse real stable inequality for any specific polynomial for all vectors in the positive orbit?
The reverse, so you mean you want greater or equal to here?
With 1.
With 1.
For everything in the positive orbit. Is that possible or is this some rare phenomenon?
I guess you can do it. We have this, this is sort of a special case of this negative lattice condition, which is very common in when you're dealing with positive association.
Okay. Other questions? Not, let us thank the speaker again. And we reconvene at 10:30, which is in like